Yeah, I guess a consequence of this definition is that if a momentum changes, then it's equal to a mass times a final velocity minus a mass times an initial velocity. We did preoccupy ourselves at some length with a change in momentum. And one of the earlier demos I did was when I didn't break Kwaku's hands with the bowling ball. It was you, right? Who was it?
It was Nick.
It was Nick. Well, I also didn't break Kwaku's hands, but I also didn't break Nick's hands. Oh, it was Harry.
Yeah, it was
Okay, well. Oh, that's right. Okay, that's right. Harry. I didn't break Harry's hands. When Harry caught the bowling ball compared to the ping pong ball, Harry's hands had more. There was more. There's probably more force. What else? More. The hands took more time. That's right. And more displacement. Yeah, so we spent our unit on momentum, paying attention to the fact that Harry's hands took more time to catch the large bowling ball than they did with the ping pong ball. And we'll spend our unit on energy, focusing on the fact that he took more displacement, that there was a larger drop in distance. Yeah, and so what we said is that the change in momentum is the result of a force acting over an amount of time, and in particular, that in some cases you could take the amount of force times the amount of time. What else do we say about a change in momentum and its relationship to force?
Isn't it equal to the integral of
Yes, that's right. That the change in momentum of an object is equal to the integral of the force on it with respect to time, or the net force if there are multiple forces acting. I guess I could elaborate this thought to include multiple forces by putting a little sigma right there. Yeah, that's right. The integral of force with respect to time is called the impulse, and this is the impulse momentum theorem, that the integral of force with respect to time gives the change in momentum of something. So if you were to have force with respect to time, then I guess this blue integral would tell you the amount of change in momentum of the thing that experienced that force. What else did we say? Yep, I guess provided that the mass doesn't change, if the momentum of something is constant, it will be proceeding at constant velocity too. Nick?
What about like momentum in a system?
Yeah, what did we say there?
That's conserved when like there's no external net force. So when all
Yeah.
the forces are internal, I guess. Is the word.
Yeah, if only internal forces act in a system, if only internal forces act, then the momentum, then the momentum of the system is constant. And what is the momentum of a system? Like if I have this cart and this other cart, like how could I figure out the momentum of the system? What does that mean?
The sum of the individual momenta.
Yeah, it's the sum of the individual momenta. It's like the momentum of the first thing plus the momentum of the second thing. Great. We had one more thought that I would put up here, and it had to do with average force. Anyone remember what that was? Ian?
Isn't it delta P also equals F times F average times altitude?
Yes. And so what I'll say about that is that what an average is when something changes, like the value of a force or the value of your test scores, you can say, well, what if it hadn't changed and you just had one value the whole time? What one value could you have had that would give the same total result as the value that actually changed? The value of an average force is like this. The average force is sort of the height on this graph that will give this green rectangle the same area as the blue integral. Nick?
So when would you use the delta P equals F delta T?
Great. So
Versus when, I mean, I understand that
yeah.
when you want to know like What you just explained, I understand that, but can you explain that?
Yeah, so this is the impulse momentum theorem. It's true whenever a force or a net force acts on an object. This is the same statement as that is by the definition of what an average is. When is this true? It's actually just only true in a special case. You wouldn't always say this.
When force is constant.
Yes.
Wait, what did you say, Harry?
When force is like constant.
Yeah, so if you had, remember we sort of imagined that a chipmunk pushing on a cart, only when there's a constant amount of force acting on an object would you say that the change in momentum is equal to the value of the force times the time interval. This is the same statement as this when the force is constant. Okay? And I think that's more or less it as far as physics. We had this idea of conservation of momentum, that when only internal forces act in a system, momentum is constant in that system. What did it look like when we were solving problems using the conservation of momentum?
You did.
Rob?
You started with finding momentum before
Mhm.
in actions, and then like the moment after. You found the momentum between the two, and then that's how you found the change of. Or, yeah.
Yeah, there's always some sort of like before cartoon
Yeah.
and some after cartoon, and then we would write like an algebraic expression for the momentum before, and then we'd set it equal to an algebraic expression for the momentum after, and we'd solve for the unknown. Yep, that's right. Okay, so that's what we've done so far this unit. We also did a lab on center of mass, which we'll review today, and we'll sort of codify our understanding of center of mass. We'll have a worksheet due tomorrow, Wednesday, and then the balance of the week we'll spend with review. Okay, we did a problem earlier in the year involving a monkey, right? Did we?
Yeah, the monkey rope problem.
Yeah, there was a package of bananas on the other side. Yep. And when we drew the monkey, we drew this, right? This was our drawing of a monkey. We drew the monkey as a particle, as if all the monkey's mass were at the same location. And then we said, oh yeah, and the acceleration of this monkey is blah, 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 in terms of like the other variables of the problem. But that's not really right. It couldn't be because, you know, like the nose of the monkey would have a different acceleration from like parts of the tail of the monkey. Like the monkey has spatial extent, but we drew it like it didn't, and the motion of different parts of the monkey were different, but we drew it as if it just had one motion. And so today we're going to sort of formalize our take on what we mean when we reduce an object that has spatial extent to something not having spatial extent. In order to do that, I'm going to use the word system. And a system is just any group of particles that you want to talk about. So you could talk about the system of like me plus that flag and say that's one system. You could talk about the system of just one cart. You could talk about the system of two carts together. Any number, any choice that you make as far as what a system is, you have the right to make. If I'm going to treat a system, a group of particles, like it's just one thing with one motion, then I'll use the word object to describe it. So for example, if this bottle is moving like this, I might refer to it as like, oh yeah, what's the velocity of this object? But then if I turn the bottle like this, well, I'm not sure I would have an easy answer for the velocity of that object because different parts of it have different velocities. A system is any group of particles. An object is a group that we're treating as if it were all one thing. So forget that. So here was the first question that I asked you to consider. I didn't ask you to consider it with quite the same language then as I am now. But if we have our, let's see, half a kilogram at 80 centimeters and our 1 kilogram at 20 centimeters. Well, if we were to ascribe just one position to this setup, what is the one position that we would ascribe to it? We are sometimes in the business of ascribing just one position to an object that, or to something that has multiple locations. So what is the one position we would ascribe to that? Well, I can sort of motivate the idea that if you know where something is, you can hold it from underneath. If you get the right answer to the question, where is something, then you can hold it from underneath. And so where is this setup? Where can I put my fingers to hold it from underneath? Caleb?
The center of mass.
Yeah, the center of mass. And where is the center of mass of this? 1 kilogram at 20 and half a kilogram at 80. Do you remember? We had a formula. It's true.
The center of mass equals m1 times x1 plus m2 times x2 over m1 plus m2.
That's true. And you could do that with your calculator right now. Anyone able to do this without using your calculator? Henry?
Yeah, I think, did I say what I think the answer is?
Please.
Like 30.
How'd you do it?
I took the half to the whole ratio of the
Mm-hmm.
and then multiplied that by the difference and added it to the one. No.
How-
Oh no, would it be 40?
Yeah, so let's see. They're how far apart from each other? And the center of mass is like a third of the way from here to there, 2/3 of the way from there to there. So yeah, 40. And indeed, there it is at 40. When you know where something is, when you do a good job ascribing one position to something, you can hold it from underneath. So there's my hand under 40. And why do I need a few fingers worth of thickness in order to do this right now, Caleb?
It's not taking into account the meter stick.
Right, it's not taking into account the mass of the meter stick, which we could treat as a third object located at its center of mass, 50 centimeters. Oh boy. Okay. Kabloop. So here, I would say don't copy down this slide until I start saying it. Some of the explanation we're going to do verbally, but I just kind of overwrote it for people who are seeing this at home. So this 1 kilogram is 2/3 of this total mass. This mass is 1/3 of this total mass. And so we got 40 centimeters using the reasoning that Henry suggested. If I go down that same line of reasoning for mass m1 at position x1 and mass m2 at position x2, we already did the algebra for this in class. So I'll just algebra cadabra us right to the same place. Start here and go some fraction of this distance where that fraction is dictated by the fraction of masses at different locations. Then do. There it is. Now, maybe resume note-taking. The center of mass of two objects is m1 x1 plus m2 x2 divided by the total mass in the system. And so if I do that, then here's just a calculation of showing how to use this formula. Everybody have this down? To find 40 centimeters again. So it's kind of like I'm holding a 1.5 kilogram object whose location is right at 40 centimeters. Okay? Okay.
So if you take away the initial 2 and add it to the equation, then
Correct. Yep, that's right. And what one position would I ascribe to the meter stick? Would it be 0 or 50? That's right, because you're treating it, if you were to ascribe just one position to an object, you ascribe it the position of its center of mass. Alrighty. Let's give you guys a break. All right, different setup. Where's the center of mass of this? Anyone I haven't heard from yet? If I have two equal masses, some separation, what is the location of the center of mass? I think I've heard from almost everyone. Joe, can I pick on you? Where's the center of mass of this duo of objects?
It's right in the center.
Yeah, right in the center of them. Great. And we already said that if we have twice a mass and then another mass over there, then the center of mass is closer to this one, 1/3 of the way from here to there. I'm going to relate this concept, the center of mass, to the concept of weighted averages, which I think you may have met before. You know that this does not work, our grading does not work with weighted averages in this class. We don't use weighted averages in calculating grades, we use total points. But in a different class, if you had a quiz grade of 86 and a test grade of 92, and quizzes were 30% of your grade and the rest was test, what would you put into your calculator in order to calculate your average in this class? Michael?
We did 92 times 0.7
Uh-huh.
plus 86 times 0.3.
Yeah, that's right. You take the 30% times your quiz grade plus the 7% plus the 70% times your test grade. What are those? Those things that I've just revealed, underlined in. Those are the weights. That's right. Those, and yeah, they're the percents. I would say this is the weight accorded to the quiz average, and this is the weight accorded to the test average. I've underlined the weights in red. And so now I'm going to relate this back to our formula for center of mass, if you don't mind, and try and show you that this is a weighted average. What does the x1 get multiplied by? Well, this, but then it also gets divided by this whole denominator, right? And what does the x2 get multiplied by? Well, m2, but then divided by this whole denominator. So are you okay with this expression being written this way?
Yes.
Same way, it's just,
Just the weight takes an average and you multiply it by the.
and so check it. These are weights. This is a weighted average of position. What weight is accorded to this position? Well, it's the fraction of the total mass at that position. And what weight is accorded to this position? Well, it's a fraction of total mass at that position. A center of mass is the average position, but it's a weighted average by mass. So that's neat. Let me just revisit this one more time. If I call this position x equals 0, then let's see, what's the average position? Well, 2/3 of the mass is there, so I can multiply 2/3 times that position of 0. And 1/3 of the total mass of this system is at that location, a position I'll call x equals d. And so 1/3, or m over 3m, gets multiplied by d. So the average position here is 1/3 of this distance from there. Nick?
This doesn't really have, I mean, it's about center of mass, but it's not something I'm guessing we're learning. But
Mhm.
does, like the distribution of mass in like an object with like a complex shape, does that matter when you're trying to find the center of mass? Like if you were to hold like a, do you see what I'm asking?
I wonder if maybe you're wondering about something that's two-dimensional? Tell me a little bit more.
I'm just saying, like, I'm just thinking about like,
There's a star.
yeah, or like I was thinking about the center of mass of like a monkey who like,
Mhm.
like a bunch with his arms out here and whatever. Like,
Yeah.
does that affect?
Point.
Or
Yeah,
does it
so-
not really matter? It's the same.
Well, no. Oh boy.
Yeah, with one finger. Yeah, sure.
Yeah. Yeah. So I guess like I think that like my average position is roughly like here, and then if I go like this, I do think that I have changed the average position of the bits of my body to being more to the right now. And now I've probably made it so that the average position is down my midline once again. So yes, absolutely. It's an average of position weighted by mass. Okay. All right. We also talked about this, how, and in fact, we didn't even have to talk about it. You were able to just guess this. When I asked you to write down what you think the center of mass formula is for 3 or more masses, and then to test it as part of the lab, I think you generated this. And so look, this is still a weighted average where each position gets multiplied by the mass at that position divided by the total mass. The third position gets multiplied by the mass at the third position divided by the total mass in the system. Okay. So now I'd like to talk about how the center of mass of a system can move. And if this is the formula that we've had for the position of the center of mass, would anybody like to guess a formula for the velocity of a center of mass? Let's take a step back, actually. Independent of that, can anybody imagine wearing like some kind of augmented reality, like a Google Glass or something like that? And can you imagine it showing you a red dot that shows the position of the center of mass of the blue and the red cart? Where is the red dot right now? It's right in the middle. And where's the red dot now? Yeah, closer there. And so red dot's back in the middle. We're imagining this red dot. What happens to the red dot when I start moving this cart? It's moving. The red dot showing the center of mass moves. You could talk about its velocity. You could talk about the velocity of that center of mass moving, right? It has a velocity in meters per second that you could measure. So a center of mass can move. And let's see, is the center of mass moving faster or slower now compared to now? When was it moving faster? Yeah, it was moving faster. And so the center of mass velocity depends on the velocities of the individual objects. And could you intuit a formula for the center of mass velocity? Caleb?
M1, V1, X1 plus M2, V2, X2 over M1, V1 plus M2, V2.
I don't think that would have the right units. I think the thing that you just quoted to me has units of position, because it sounded like the M's and the V's canceled in the numerator and denominator. Anyone who happens to be in a calculus class, what if you took the derivative of both sides of that equation with respect to time?
What if? Like, what do you mean?
Should we do it?
So the velocity of the center of mass, what would happen to the m's if you took the derivative with respect to time? Nothing? They're just constants. What would happen to the x's? And what is a dx dt? It's a velocity. It's a v. That's right. Yeah, the velocity of the center of mass is a weighted average of the velocities in a system. So just to have a quick example, would you take a minute and I'll take attendance. Calculate this. If we got a 1 kilogram cart moving with a velocity of 3 meters per second and a ½ kilogram cart moving with a velocity of negative 1 meter per second. Yep, it was a trick. It's a trap. All right, please calculate the velocity of the center of mass of that business. you feel like you have an answer, see if you can write it down and get your neighbor to agree with you. All right, what did you guys end up thinking? Nick? 5/3? I think that's right. So let's see, we got
Nice.
doop, right?
Yeah, you tiny ears. Bill was, he's tiny.
Oh, sorry.
They're like baby ears.
All righty. Yeah. What's the momentum of the system, by the way? How could you get it?
Isn't it just the second part without the division?
Wait, are we saying after they collide?
No, before. The momentum of the system, you're recognizing that it's just this numerator?
Yeah,
Why?
because it's M1V1 plus M2V2.
Yeah, isn't that something? Yeah, you get the momentum of the system by adding up the individual momenta of the carts. But look, you see how the momentum of the system sort of lives in that expression? What other expression gives the momentum of the system? I didn't ask that very clearly, but check it out. This is the momentum of the system. This is the momentum of the system. If you take the mass of the system and multiply it by what velocity? You get the momentum of the system. Yeah, the center of mass velocity. So if you were to have a system of two carts and you were to ascribe just one mass to them, it would be their combined mass. And if you were to ascribe just one velocity to them, it would be which velocity? The velocity of the center of mass. If you ascribe just one position to a system, you're talking about the center of mass position. If you ascribe just one velocity to a system, you're talking about the center of mass velocity. And so look, now we have like another way to calculate the momentum of the system. You can add up the individual momenta, or you could treat it as one grouped object with one velocity, and that velocity is the center of mass velocity. That's kind of neat. Good old math. Yeah, so the momentum of the system is the sum of the individual momenta. It's also the mass of the system times the velocity of, what about the system? The center of mass. Center of mass is what happens when you treat multiple things as just one thing. So there's, whatever. You can do the calculation yourself. Okay. We have just talked about how the center of mass can have a velocity, and the center of mass velocity relates to the momentum of a system. And so now we're going to talk about how the center of mass can accelerate. Can you see the red dot there? If I'm accelerating one of these carts, then the center of mass has an acceleration. And would you care to guess an expression for the center of mass acceleration?
Take the derivative again.
Yeah, let's take the derivative again with respect to time and kablamo. The acceleration of the center of mass is equal to the weighted average of the different pieces of acceleration of the system. There was a moment in the last slide where you realized that you could talk about the momentum of the system by treating the system as just one object whose velocity was the center of mass velocity. I'm going to do some stuff that leads to a similar result having to do with acceleration. You don't need to copy down all of the steps, but I hope that you'll follow them. How did I go from this line to this line? Bucket? Ian? Yeah. Let's, in the spirit of review this week, let's review one more time Newton's laws and the numbers associated with them. What does Newton's second law say?
Acceleration equals sum of forces over mass.
Yeah. Great. What does Newton's first law say? It basically does, yeah. Newton's first law says that an object in motion stays in motion unless, yeah, in other words, if there is no external force on an object, then what about the velocity of the object? Constant. Do you see why this idea is already in this idea? Why?
Zero. If the acceleration is zero, then
Yeah, that's right. This line already includes the idea that if the net force on something is zero, its acceleration is zero, and so its velocity is constant. But historically, this idea came first. It came from Galileo, and then this came from Newton. And what was Newton's third law?
Equal and opposite forces.
I agree. Yeah, if,
same type, same magnitude, different direction.
yeah, that if object A exerts a force on object B, then object B exerts a force on object A at every instant of the same magnitude, opposite direction, and the same type. This is a surprising result. It's true no matter what's accelerated, whether or not something is accelerating, whether or not something is alive, whether or not something is bigger than the other thing. The force that I exert on the squirrel is the same as the force that the squirrel exerts on me. Yeah, yeah, you can't defeat that squirrel. Believe me, I've tried, but Newton's third law. I was once walking around school with my daughter, and it was a little more than a year ago, so she was in her mid-twos. She found a closet of cleaning supplies,